Humanity has always looked up at the stars with wonder. Are we alone in this vast universe? This question drives our deepest curiosity. It fuels our relentless exploration of the cosmos. In recent times, incredible discoveries have brought this ancient question into sharper focus. We are truly living in an extraordinary era of astronomical advancement. The universe is slowly, but surely, beginning to reveal its most captivating secrets. Scientists are now finding planets beyond our own solar system almost every single day. These distant worlds are known as exoplanets. Many of these newly identified celestial bodies are unlike anything we currently know within our familiar solar system. Some are colossal gas giants, even larger than our own Jupiter. Others are smaller rocky worlds, perhaps similar to Earth. The sheer, ever-increasing number of these exoplanets is astounding. This abundance strongly suggests that planets are not a rare cosmic occurrence. Among this diverse collection of exoplanets, some orbit their host stars at a very specific distance. This particular region is often referred to by scientists as the habitable zone. This is because it's not too hot and it's not too cold for a planet located there. It's just right for liquid water to potentially exist on the planet's surface. Finding planets within this special zone is therefore a key initial step. One star system in particular has recently captured the imagination of astronomers and the public alike. This system is called Gliese 667. How do we actually find these distant worlds so incredibly far away from Earth? Discovering them is a remarkable testament to human ingenuity and our technological prowess. One of the primary methods used is called the transit method. Imagine watching a star and noticing a tiny, almost imperceptible dip in its light. This subtle dimming can occur when an orbiting planet passes directly in front of its star from our perspective. Our advanced telescopes are now sensitive enough to detect this minuscule change in brightness. Another powerful technique for detecting exoplanets is the radial velocity method. You might also hear it called the wobble method. A star isn't perfectly still when it is orbited by one or more planets. The gravitational pull of these planets causes the star to wobble slightly in space. We can detect this subtle back-and-forth movement by carefully analyzing the star's light. Dedicated space telescopes have truly revolutionized this exciting field of exoplanet hunting. NASA's Kepler Space Telescope, for instance, was an absolute game-changer. It patiently stared at a single patch of the sky for several years. During its mission, it identified thousands of potential exoplanet candidates, transforming our understanding. Now, the TESS mission, which stands for Transiting Exoplanet Survey Satellite, is scanning almost the entire sky. TESS is specifically designed to find planets orbiting nearby bright stars. These discoveries provide excellent targets for more detailed follow-up studies. Let us now turn our attention to a particularly intriguing star system, Gliese 667. This system is not just a single star like our Sun, it is actually a triple star system. Imagine looking up into its sky, you might see three suns. Two of the stars, Gliese 667a and Gliese 667b, are K-type stars, somewhat smaller and cooler than our Sun. They orbit each other relatively closely. The third star, and the one that interests us most, is Gliese 667c. This star orbits the main pair at a much greater distance. Our primary focus within this triple system is the star Gliese 667c. It is an M-dwarf star. M-dwarfs are much smaller, dimmer, and cooler than stars like our Sun. For a long time, astronomers thought M-dwarfs might not be good places to look for life. However, our views on M-dwarfs have changed dramatically in recent years. Because they are less luminous, their habitable zones are much closer to the star. This makes planets in these zones easier to detect using methods like the transit technique. Gliese 667c, despite its modest nature, has proven to be a star of great interest. The initial discoveries around Gliese 667c generated a huge amount of excitement within the scientific community. Among the planets discovered orbiting Gliese 667c, one in particular stands out. Gliese 667cc. This exoplanet is classified as a super-Earth. This term means it is more massive than Earth, but significantly less massive than ice giants like Uranus or Neptune. Its estimated minimum mass is about 3.8 times that of our own planet. Discovering a rocky world of this size was exciting in itself. The most compelling aspect of Gliese 667cc is its location. It orbits squarely within the habitable zone of its host star, Gliese 667c. As we've discussed, the habitable zone is that crucial region around a star where temperatures could allow liquid water to exist on a planet's surface. For a cool M-dwarf star like Gliese 667c, this zone is much closer to the star than it is for our Sun. Gliese 667cc orbits its star in just 28 Earth days. This short orbital period means its year is less than one of our months. Its proximity to the star, combined with the star's lower luminosity, places it in that potentially life-friendly temperature range. The initial discovery of Gliese 667cc and its prime position in the habitable zone sparked considerable hope and speculation. Gliese 667cc became a symbol of this exciting new phase in our exploration of the cosmos. Section 5. More candidates in Gliese 667, CE and CF join the list. The story of Gliese 667c's planetary system became even more intriguing with further analysis. It wasn't just Gliese 667cc that caught the attention of astronomers. Subsequent studies and reanalysis of observational data suggested the presence of even more planets orbiting this M-dwarf star. Two of these additional candidates, named Gliese 667ce and Gliese 667cf, also appeared to orbit within or very near the star's habitable zone. This was a remarkable finding. A single, relatively unassuming star potentially hosting a whole family of planets in its most promising region for life. This discovery significantly amplified the system's importance. The detection of Gliese 667ce and cf, alongside cc, painted a picture of a remarkably packed habitable zone. Gliese 667ce was estimated to have a minimum mass around 2.7 times that of Earth, orbiting with a period of about 62 days. Gliese 667cf, also a super-Earth candidate, was thought to be of similar mass, with an orbital period of around 39 days. The methods used to infer their presence relied on subtle gravitational tugs on the star, the radial velocity technique, which requires incredibly precise measurements. The idea of multiple planets clustered within a star's habitable zone is incredibly exciting from an astrobiological perspective. If one planet in the zone offers a chance for life, then having several such candidates in the same system statistically increases those odds. The Gliese 667 system, even with some uncertainties, pushed the boundaries of our understanding. Section 6. Life's hurdles, challenges in the Gliese 667 system. While the prospect of multiple planets in the habitable zone of Gliese 667c is thrilling, we must also consider the challenges life might face there. M-dwarf stars like Gliese 667c present a unique set of environmental conditions. One significant factor is tidal locking. Because planets in the habitable zones of M-dwarfs orbit very close to their star, they are likely to become tidally locked. This means one side of the planet would perpetually face the star, experiencing constant daylight. The other side would be locked in eternal darkness and cold. This phenomenon of tidal locking could create extreme temperature differences between the day and night sides of a planet. Another significant challenge associated with M-dwarf stars is their tendency to produce powerful stellar flares. These are sudden, intense bursts of radiation, including X-rays and charged particles. Section 7. Beyond Gliese 667. The richness of M-dwarf systems. The Gliese 667 system, with its intriguing collection of potential worlds, is not an isolated case. It serves as a fantastic example of a broader trend. M-dwarf stars, those small, cool, red suns, are now understood to be incredibly important in the search for life beyond Earth. As mentioned earlier, M-dwarfs are the most common type of star in our Milky Way galaxy. They make up roughly 70 to 75% of all stars. This sheer abundance means that if M-dwarfs can host habitable planets, then the number of potentially life-bearing worlds in our galaxy could be truly enormous. Another compelling advantage of M-dwarf stars is their incredibly long lifespans. While our Sun has a total lifespan of about 10 billion years, M-dwarfs can continue to burn their hydrogen fuel much more slowly and efficiently. They can shine steadily for hundreds of billions or even trillions of years. This extended period of stability could provide a much longer, more tranquil window for life to originate, evolve, and perhaps even develop complexity on any suitable planets orbiting them. Time is a key ingredient for evolution, and M-dwarf systems offer it in abundance. Section 8. The search continues. Future telescopes and techniques. Our exploration of exoplanets and the search for life beyond Earth is only just beginning. The discoveries made so far, including those in the Gliese 667 system, have laid a crucial foundation. But what comes next? The future is incredibly exciting, driven by the development of new, even more powerful telescopes and innovative observational techniques. One of the most anticipated instruments is the James Webb Space Telescope, or JWST. Launched a few years ago, JWST is already revolutionizing astronomy with its incredible sensitivity, particularly in infrared light. This capability is key for studying distant exoplanets. The James Webb Space Telescope has the remarkable ability to analyze the atmospheres of some exoplanets. As a planet transits its star, a tiny fraction of the starlight passes through the planet's atmosphere, if it has one. Different gases in the atmosphere absorb specific wavelengths of light. JWST can detect these absorption patterns, effectively taking a chemical fingerprint of the planet's air. Scientists will be looking for biosignatures, gases like oxygen, methane, or ozone, in combinations that might indicate the presence of biological processes. Beyond JWST, the next generation of enormous ground-based telescopes is also on the horizon. Observatories like the Extremely Large Telescope, or ELT, currently under construction in Chile, will have mirrors tens of meters across. These colossal telescopes will provide unprecedented image sharpness and light-gathering power. Section 9. Conclusion. A universe brimming with possibility. Our journey through the cosmos, from asking ancient questions to making concrete discoveries of new worlds, has been extraordinary. We have moved from pure speculation about life beyond Earth to identifying specific, tangible targets for our search. Systems like Gliese 667, with its multiple super-Earth candidates in the habitable zone, represent milestones in this grand endeavor. They show us that the building blocks for potentially habitable planets are widespread. They fuel our optimism that we might not be alone in this vast expanse. The universe, it seems, is far more generous with planets than we once thought. The implications of finding life beyond Earth, even if it's just simple microbial life, would be truly profound. It would reshape our understanding of biology, showing that life is not a unique fluke confined to our planet. It would also fundamentally alter our perception of our own place in the universe.